All right, let's talk about the rivers and bridges activity. We talked about last time we talked about Euler circuits and Euler trails, which come from a man named Euler, Leonard Euler, who kind of um, introduced this idea of, or he solved a problem that has to do with rivers and bridges that was essentially solved by this theorem that he kind of produced after solving that problem. So we're going to look at examples similar to what he solved in this rivers and bridges uh, activity worksheet, if you can call it that. But this is the specific problem that Euler solved in the 1700s. It had to do with the city of Königsberg in Poland, I think. And there was a problem posed in some mathematical journal about this town, which had a river run through it, or a series of rivers kind of run through it, with some bridges. And the question that was posed was whether it was possible to cross each of the bridges once and only once while walking around the city of Königsberg. So the question was, can you start anywhere in the city? So that would be in this area, this area, this area of the city, or this area of the city. Can you start anywhere and cross these bridges in a way that you cross every bridge exactly once? And it turns out that Euler essentially solved that problem and proved the solution using the idea that the number of bridges and the number of areas that the city has makes it so that this is an impossible. It is impossible to cross each bridge once and only once. Um, so we can actually answer this question now that we know what the Euler circuit requirements are, or an Euler trail or an Euler circuit requirements are, by just converting this picture of the city or the map of the city with the bridges given into a kind of graph. So we can kind of ignore this part because we know how to do this already. But let's simplify the problem and draw this into a graph where what does it say? Where each area of land is a point, and each bridge is an edge joining two points. So if I were to convert this into a graph, I would say this whole top area of land for this city is going to be a single point on my graph, right? And then we're going to do the same thing for each area in this city. So that'll be a point. This area over here will be a point, and then finally this eastern area of the city will be another point. Right? So our graph is going to have 4 vertices, and we can draw edges connecting these vertices based on if there's a bridge connecting those two areas, right? So this bridge here, which connects this large area to this large area, is going to be an edge connecting these two vertices, right? You can draw it going through the bridges if it helps you keep track of which bridges you've accounted for. So we'll do that. So every bridge is gonna equate to an edge. So I can draw this edge, which connects the bottom left area to the middle area. There's actually another bridge connecting those two dots, right? And then from that middle area, we have an edge to the top area. We have another bridge to the top area, and then we have a bridge to the right area. And then finally, we have this bridge that connects the top area to the right side area, right? So these are all of the edges and vertices representing all of the areas and the bridges in the graph, or in the city. And then once I've drawn this on top of the city, it might be a good idea to transfer this into a simplified version of this by doing more of a smaller graph where we use straight line for the edges if we can. So for example, when I transfer this over here, I know there's only one edge connecting these two vertices. There's only one edge connecting these two vertices. And there's only one edge connecting these two vertices. And then there are parallel edges when it comes to these vertices over here on the left. All right, so I can kind of draw a simplified version of this graph here. These are the same graph. One is just drawn on top of the picture with the rivers, but it might look a little bit confusing. It might be hard to count the edges and stuff. This is going to be a lot easier to work with when it comes to counting edges and degrees of vertices and answering the question of whether or not there is an Euler circuit or trail. So we're going to answer the question of Euler circuit. And Euler trail. All right, we're going to answer both of those questions for this graph. And to answer that, we need to count the degrees of the vertices. So this northern vertex has a degree of 3. The eastern vertex has a degree of 3. The southern vertex has a degree of 3, and the middle island vertex has a degree of 1, 2, 3, 4, 5. All right, so looking at those vertices and their degrees, we see that they are all odd. There's not, remember for Euler's circuit, they all have to be even. So this one is a no. And for the Euler trail, the theorem or the rule was that there had to be exactly 2 odd vertices and the rest had to be even. So the Euler trail answer is also no in this situation. So that's going to be our answer, actually combined with the graph, I guess. So all of this is kind of our answer. Right, so this is what we're going to do on this kind of activity sheet. There are examples of different cities that have rivers running through them and bridges over those rivers. And it gets pretty complicated when you get to this last one. There are a lot of bridges. There's not that many areas to the city, so there's 1, 2, 3, 4, 5, 6 areas to the city. But there are a lot of bridges, so there's going to be a lot of edges. So the thing I did where I drew the graph on top of the city may not be super viable to do, but if it helps you transfer to a smaller graph or a simpler graph, then please go ahead and do that. Otherwise, I do recommend you draw a graph, an illustration of it, not on the actual city itself, but on the side somewhere, and then answer these 2 questions for each of these cities. You don't necessarily have to answer all of these questions. You can consider some of these questions, although I'm not looking for you to answer them. For example, adding bridges to make it so there is an Euler graph, or an Euler circuit, or an Euler trail. So if the question here was if we added an edge somewhere, if we added a bridge, or if we removed the bridge, would it be possible to have an Euler trail or an Euler circuit? And you can consider that by saying, okay, what happens if I remove this bridge in this city? So if I were to remove this bridge, then this degree would reduce down to 2, this degree would reduce down to 2, and we would have the rest of them would be unchanged, so we would have these degrees. And then the answer to the trail question would become yes, because there are exactly 2 odd vertices, right? So you can consider questions like that where it'll say, do you think adding a bridge or maybe removing a bridge? I think they all say adding a bridge. Yeah. What happens if we add a bridge in a certain area? Does that make the graph have an Euler trail or an Euler circuit if it doesn't already have one? So this is essentially what I want you to work on, as far as what you need to do for this worksheet. Just draw the graph for the given city, and then answer these two questions. And then you can also answer these questions if you would like. Do you think adding a bridge would change your answer? Do you think adding bridges would change your answer? Is there one on the last one? Not really. Okay. So this is something that you have to work on now. You also have the worksheet from last time with a bunch of graphs. If you didn't finish that last time, you can work on it. This is what you were supposed to do on that one: number of vertices, number of edges, number of loops, and then determine whether there's an Euler circuit or trail or neither, and then give the example of an Euler trail or circuit if there is one. So give the pathing of the trail or circuit. Right. Are there any questions on the city with the rivers example that I went over? Or are there any examples at all? Or are there any questions at all?